This is Chapter 2, Section 6, Problem Solving Using Unit Conversions. So why do we need conversion factors, and how do we put them into practice? Remember that since a conversion factor is equal to 1 by definition, we can multiply any quantity by such a factor to convert from one unit to another. So for example, if we know that a child weighs 23 kilograms, how do we calculate how many grams this is? To answer this question, you must know the relationship between the two units, kilograms and grams. 1 kilogram equals 1,000 grams, because kilo means 1,000. From this relationship, we can obtain two conversion factors, 1 kilogram per 1,000 grams, or 1,000 grams per 1 kilogram. However, only one of them will actually be useful to solve this problem. How do we know which one? Let's see what happens when we multiply the given weight by each of these two conversion factors. So we have 23 kilograms times 1 kilogram per 1,000 grams, or we have 23 kilograms times 1,000 grams per kilogram. Let's see what happens when we solve each of these possibilities. When you multiply numbers with units, you can separate them into the numerical part and the unit part. So 23 divided by 1,000 becomes the numerical part, and the unit part becomes kilograms times kilograms divided by grams, as you can see here. For the second one, you have 23 times 1,000 as the numerical part, and then kilograms times grams divided by kilograms as the unit part. For the first one, 23 divided by 1,000 gives you 0.023, okay, but then the unit becomes very strange. Kilograms times kilograms is kilograms squared, and then you're still dividing by grams in the denominator. So this is the unit that we would get. For the second one, we have 23 times 1,000, which equals 23,000, but then you can see that the kilograms cancels on the top and the bottom. That leaves us with just the grams unit left, and so our answer would be 23,000 grams. This obviously makes a lot more sense in terms of the unit that we're looking for. We started with kilograms and we wanted to convert it into grams. So the bottom conversion factor was the correct choice because it makes the units work out correctly. The first conversion factor wasn't appropriate for this context. Mathematically, that still has some sort of meaning, but it doesn't really make sense when we're dealing with measurements. The process of problem solving in chemistry often requires one or more conversion factors to change a given unit to the needed unit. That means you're probably going to need to follow a few steps. First, you have to identify the units that you're starting with. Then you have to determine the units that you want. And then you have to find relationships that connect the given unit to the desired unit. Here's another example of converting weight, but this time we're not sticking to the metric system, we're converting from the US system to the metric system. So if a person weighs 164 pounds, what is their body mass in kilograms? Again, the strategy that we need is to identify the unit that we're given, which is pounds, 164 pounds, and the unit that we need, which is kilograms, and then figure out the relationship that relates pounds and kilograms. The plan in step 2 is very simple for a case like this, but later on when we see that you need to chain together multiple conversion factors, it can be a lot more useful to understand this plan ahead of time. For now, all we need to know is that you can take pounds, multiply it by a conversion factor, and you'll end up with kilograms. Next, we need to find that equality that represents that conversion factor. We need to know how kilograms relates to pounds. This isn't something that you're expected to remember, but if you need it, you'll be shown that 1 kilogram equals 2.20 pounds. Remember that this 2.20 is a measured number, by the way. From this equation, we can get two conversion factors, 2.20 pounds per kilogram and 1 kilogram per 2.20 pounds. Then the last step is to set up the problem, take the weight, multiply it by one of these conversion factors, and find the answer. Again, how do we know which conversion factor to use? We have to look at the units. You multiply pounds by a conversion factor that will cancel pounds and leave behind kilograms. So if the pounds unit is on the top in your original measurement, it needs to be in the denominator in your conversion factor. That way, when you multiply them together, the pounds will cancel out. The kilograms, which is the unit that you want, has to be in top of the conversion factor so that it ends up being left over when you're done. So you take 164 pounds and you have to multiply it by this second conversion factor, 1 kilogram per 2.20 pounds. You end up with an answer of 74.5 kilograms once you round to the appropriate number of significant figures. Here's another example. A rattlesnake is 2.44 meters long. How many centimeters long is the snake? I'll give you a few seconds to pause the video and try this on your own before I show you how to do it. Alright, so this is a relatively easy one. It's a simple conversion between meters and centimeters, but it's still pretty easy to get confused as to whether you're multiplying or dividing by 100. Understanding how the units work out can resolve that confusion. You start with the measurement you're given, 2.44 meters. And you know that you need to multiply it by some conversion factor because you're trying to convert units. Remember, every conversion factor is a ratio, so when I set up problems like this, I put in this form of a ratio where you have a top and a bottom. And then I think about how I can get rid of the meters unit and leave the centimeters unit. Meters is up here, so that means I need to cancel it by putting meters in the denominator of my conversion factor. The unit that I want is centimeters, so I need to put centimeters on top in my conversion factor. Once I know that this is where the units go, then I can think about the relationship. I could think about the relationship first and then try and figure out which of the two conversion factors to use, but to me it's easier to do it this way. Now I know that 1 centimeter equals 1/100th of a meter, so I could put the numbers in this way, but it's a little easier to simplify this to the more common version, which is 100 centimeters equals 1 meter. From this equation, now all I need to do is fill these numbers into the conversion factor that I've already begun to set up. The top of the conversion factor is centimeters, so from the equation I take 100 centimeters and I put it on top. The bottom is meters, so from the equation I take 1 meter and I put it on the bottom. That means that the conversion factor that I need to use is 100 centimeters per meter. 2.44 times 100 is 244. Meters cancels out, and I'm left with the centimeter unit. So it's 244 centimeters. The slides take you through the method of doing it that you saw previously, where first you analyze the problem to figure out what you have and what you need. Second, you set up a plan to figure out the conversion factors. Third, you use the equation between the units to figure out the conversion factors. And fourth, you set the problem up and solve it. As I mentioned, you'll often need more than one conversion factor to solve a problem in this class. In many cases, you'll need 4 or 5 or more conversion factors, and you'll have to keep the units in them straight so that they end up with the correct unit at the end. When you set up these problems, you're simply multiplying together a string of conversion factors one after the other. The best way to do it is to arrange them so that the unit on top in one conversion factor cancels the unit on the bottom of the next conversion factor in line. Here's an example of this. A doctor's order prescribed a dosage of 0.150 milligrams of Synthroid. If tablets contain 75 micrograms of Synthroid, how many tablets are required for this dose? take a few minutes to pause the video and try this out on your own. Then you can come back and see how we do the answer. All right, so we can think about this the way that the slides have us do, which is to first analyze the problem. We know that the dosage prescribed is in milligrams of Synthroid, a drug. And we know at the end we want to figure out how many tablets we have to give the patient. The tricky part about this question is that it doesn't tell us how many milligrams of Synthroid are in a tablet. Instead, it tells us how many micrograms are in a tablet. So that should tell us that we need to use the microgram unit as sort of a bridge or a connection between milligrams and tablets. So we're going to go from milligrams of Synthroid to micrograms of Synthroid. And then we can go from micrograms of Synthroid to tablets of Synthroid. Setting up the plan in this way shows us that we're going to need 2 conversion factors. Then we can look at the problem to try and figure out the equations that will give us what we need. Again, an easy way to do this is to start with the quantity that you're trying to convert, in this case 0.150 milligrams of Synthroid, and then multiplying it by conversion factors and putting the units in a way that it'll work out. I know from the plan that I'm going to need 2 conversion factors. So I have one ratio here, and I have a second ratio here. I know at the end I want my unit to end up being tablets. And so this actually is going to begin to tell us what conversion factors we need to find. Our initial measurement is in milligrams of Synthroid, so the first conversion factor should cancel milligrams of Synthroid. Remember that we're going through micrograms of Synthroid as the intermediate, so that should be what we first transform milligrams into. So here will be micrograms of Synthroid. The next conversion factor then should cancel this new unit that we put on top. The top of the first conversion factor is micrograms of Synthroid, so that's what we're going to need to cancel in the second conversion factor. Finally, since we know that these are the only 2 conversion factors we need, the top of the second conversion factor must have this final unit we're looking for, which is tablets. Doing it this way, we can ensure that the units work out, and it can also tell us which relationships to look for in the question itself. The first conversion factor is telling us to look for a relationship between milligrams of the medicine and micrograms of the medicine. Now in this case, that information is not in the problem because it is something that you should know from your understanding of metric prefixes. A milligram is 1/1000th of a gram, and a microgram is 1/1,000,000th of a gram. So a milligram is 1,000 times larger than a microgram. In other words, a milligram equals 1,000 micrograms. From that metric equation, we can put these numbers in. Micrograms goes on top, so that's where the 1,000 goes, and milligrams is on bottom, so that's where the 1 goes. The second conversion factor tells us that we need to look for a relationship between micrograms of medicine and tablets. That is in the question. It says tablets contain 75 micrograms of Synthroid. The way that you would express that as an equation is 1 tablet equals 75 micrograms of your drug, Synthroid. So from this equation, we can see that the 1 goes on top here, and the 75 goes in the denominator here. Looking just at the units, we see that milligrams of Synthroid cancels milligrams of Synthroid. Micrograms of Synthroid here cancels micrograms of Synthroid here. And indeed, we're left with just the tablet unit at the end. Then we can take our numerical part. 0.150 times 1,000 is going to give us 150. And then divide that by 75, and we end up with 2 tablets. And that's our answer. Again, the slides take you through the same process in a little bit of a more detailed step-by-step approach, but it's the same idea. You're going from milligrams to micrograms to number of tablets. And again, you end up with the same answer, 2 tablets. Again, conversion factors are extremely important for this class. We're going to use them from today until the very end of the class. So it's important to practice these and get the hang of it so that you can do them relatively quickly. So let's do another example. How many minutes are in 1.4 days? Now, we're converting a length of time from days to minutes. If I happened to know how many minutes are in a day, then I could make this a simple one-step conversion. But I don't remember that number, and I don't see any reason to bother remembering that number. Instead, I do know some relationships. Since these are simple relationships, I can actually start by writing those. It doesn't really matter whether you start by writing those or start by writing the equation out. But let's start by writing those. I know that 1 day equals 24 hours. And I also know that 1 hour equals 60 minutes. What this tells me is that the way that I convert from days to minutes is by going through an intermediate unit of hours. If you're still not sure about that, or you can't come up with those relationships on your own from the beginning, it can still help to start with the quantity that you're given, 1.4 days, and think about the conversion factors that you need. If you want to convert days to minutes, in the best case, you could do it in one step with one conversion factor. You want to cancel days, so days would go in the bottom, and you want to end up with minutes, so minutes would go on top. When you see this, though, you should start asking yourself a question. Do I know the relationship between days and minutes? In this case, I have to say no, I don't know that relationship exactly. So that means that I need to forget about minutes going on top here, and instead think about doing a second conversion factor, where minutes will be on top there. However I do it, minutes have to end up being on top because that's the unit I'm looking for. My answer needs to be in minutes. So at this point, you do have to understand something about how days and minutes work, and that there is a connecting unit between them that you do understand. That connecting unit, again, is hours. So if I know that days can be converted into hours, and then hours can be converted into minutes, then I know the process, the plan for getting from days to minutes. Then it's just a matter of filling in the numbers. I've already written out these equations, so it shouldn't be too hard to see that 1 day equals 24 hours is your first conversion factor, and that 1 hour equals 60 minutes is your second conversion factor. Again, these slides show you this process step by step, but I just want to skip ahead so that we can see the answer. Here we have the conversion factors and then the final expression, which is 1.4 days times 24 hours per day times 60 minutes per hour. Now, if you put these into your calculator, you'll actually find that your calculator says that it is 2016 minutes. But this has too much precision. There's 4 significant figures there, whereas our measured number in the expression is only 2 significant figures. Remember that these expressions are exact, so they don't change the number of significant figures. That means the answer has to also have 2 significant figures. We can do that by rounding 2016 to only 2 digits. Here, however, you can see another reason why it's useful to use scientific notation. If I round 2016 to 2 figures, I get 2000. But if I write it like 2000, it looks like it has only 1 significant figure. If I try and get around that by adding a decimal at the end, now it looks like it has 4 significant figures. Really, I'm in the position of wanting to indicate that this first 0 is significant, but these last zeros are not. The best way to do that is to put all of the significant figures into the coefficient of the number in scientific notation, and then express it that way. So 2016 rounds to 2.0 times 10 to the third minutes with the correct number of significant figures. Let's do one last example. Again, I'll give you a few seconds to pause the video and try and work this out on your own. I highly recommend getting a sheet of paper and a pencil if you don't already have one, and writing out this problem and working it out on paper. The question is, if your pace on a treadmill is 65 meters per minute, how many minutes will it take for you to walk a distance of 7.5 kilometers? All right, let's think this through a little bit. We know that the pace on a treadmill is 65 meters per minute. That's a speed, but for our purposes, we can think of it as a conversion factor between meters and minutes. Now it wants to know how many minutes it'll take to walk a distance of 7.5 kilometers. Unfortunately, our speed was not given in kilometers, it was given in meters. So this means that we're going to need another relationship between meters and kilometers. Essentially, what we're doing is taking the distance of 7.5 kilometers and translating it or converting it into an amount of time it takes to walk that. So we're starting with 7.5 kilometers, and at the end, we want our answer to be in minutes. Again, if we had a speed that were in kilometers per minute, we could just divide by that speed, in other words, flip the top and bottom of that ratio, and we would end up with minutes. Unfortunately, we don't have that. We have meters per minute, which means the first thing that we need to do is convert kilometers to meters. Then we can use our speed to put meters in the bottom and minutes on top to convert meters to minutes. This first conversion factor is, again, a metric conversion. So we want to know how many meters per kilometer or kilometers per meter. Most of the time it's easiest to think about taking one of the larger unit, in this case 1 kilometer, and then figuring out how many of the smaller unit that is. In this case it's easy. 1 kilometer is 1,000 meters. So 1,000 meters goes on top and 1 kilometer goes on bottom. Once we cancel out that kilometer, at this point, when we multiply 7.5 times 1,000, we're going to have our distance in terms of meters. Then we can use the speed, which is 65 meters per minute, to do the next conversion step. Remember that 65 meters per minute is really 65 meters per 1 minute, which could just be flipped into 1 minute per 65 meters. If you want, you can think about it in terms of the equation, where 65 meters equals 1 minute, and then develop the conversion factors from that, but it's the same thing. So the real question is, which number goes where? Where does the 1 go? Where does the 65 go? Well, this is the conversion factor where the units match with minutes on top and meters on bottom. So for every 1 minute, we go 65 meters. After we do this conversion factor, this meter will cancel this meter, and again, we're going to be left with the minutes unit, which is what we're looking for. So 7.5 times 1,000 divided by 65 is going to give us our answer. Let's see what it is. Again, the plan is to go from kilometers to meters, and then from meters to minutes. We need conversion factors between kilometers and meters, and then we need to use the speed as a conversion factor between meters and minutes. Once we multiply this all out, we get 120 minutes, which is 2 significant figures, just like the kilometer measurement and the speed measurement.